Okay. There was a, okay. Okay, yeah, I'll address that. But, okay, so just a reminder, there is an exam this week. So on Thursday, we'll have an exam. I have another review session tomorrow evening. If you, again, it would be, I've gotten a couple of questions so far, but it really does help me prepare for these and to hopefully help you if you send those in, send questions in so that I can address them. So I think I noticed on the practice exam that I posted earlier, there was a missing graphic. I tried to update that over the weekend, so you can take a look if that should be fixed. But yeah, okay. So again, we will not be covering any of the material we talk about today or Thursday during lecture on exam 3. So it will just be up through integration and the last section that we covered in chapter 5, I believe. So instead, but we're still going to push on ahead, and we've got some really very wonderful mathematics that we can start talking about now. We've done really the basics of calculus here. We've done derivatives, we've done integrals. Okay, these are the basic ingredients in calculus, and the real, I don't know, strength of calculus is theorems that really work with both of these concepts and give us some pretty interesting qualitative behavior of functions and integrals. So to explain all of that, I want to just do a quick review, not review really, but summary of what we've learned. We learned how to integrate in the following cases. We have a one variable. We learned this last year, or whenever you took the one variable calc. We learned how to go over a domain D of a two variable function, where D maybe was some kind of general region, not just a rectangle. And we took triple integrals over regions E of functions of three variables. And maybe I'll say D. Let me call this dA here for area and V for volume. So we've got some blob. Whatever, okay. Here's some blob. This is our D, this is our E. And what we would like to do, so this is not quite good enough. Now, what I want to say is we have 4 dimensions we're used to really working with, at least in this class. It's sort of the typical, the most familiar dimensions we're working with. We're certainly working with these, the high dimension would be the 3-dimensional case. We have a function of 3 dimensions. We have a function of 2 dimensions. We have a function of 1 dimension. But then we also have like the thing we learn in, I don't know, like middle school or something, working with 0 dimensions, right? Functions. What is the integral of a function of 0 dimensions? So let me just, I left one out. So this is, maybe let me call this the integral over I for an interval. We could also integrate a function over a point, 0 dimension. And that's just, we just evaluate. This is just evaluating the function, if you want to think of it that way. So we really have 4 dimensions. We have 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional cases. Now, however, what you'll see in all of these cases that are more familiar is what you're integrating over is sort of an open or closed but kind of dense set. So we've got an interval in the line. We've got a domain D, that's kind of filling out some dense, region here. And then we've got this kind of solid. But once you get past 1 dimension, there's a lot of, even just in 2 dimensions, there's a lot of other subspaces that you might want to consider putting right here, right? And in 3 dimensions, there are even more, right? If we're in 2 dimensions, we might want to consider integrating over a curve, not just a domain D that has kind of an interior. So what we want to do is we want to think about how we can generalize these notions. That's going to be a part of what we do now. And we're going to generalize them in 2 different ways. And I'll write this as a kind of a single integral, but the single integral can be thought of as, 1 integral, 2 integrals, 3 dimensions. I mean, once you start integrating over 10 dimensions, you don't want to write 10 integrals, right? So what mathematicians do is actually they will mathematicians generally, and we'll write, instead of writing that, we'll just write that. We'll just write 1 integral. So we want to generalize 2 things. We want to generalize the domain that we can integrate about, and we want to generalize this integrand. Okay. To generalize both of these notions. And we'll set up about 4 different new types of integrals, 2 line integrals, 2 surface integrals, that generalize the domain and generalize these integrands. And then we'll see how they work together. 4 is maybe the lower bound. We actually have a few more, but I don't spend too much time on it. So the first thing we're going to talk about is how we generalize not the domain, but this integrand. What other things could we integrate? Well, one thing we can integrate is a vector field. Okay, so let's ask this question. I'm going to ask the question first. So here's the question. So this is a motivating question. So, okay, so what is the velocity? My chance to be poetic. What's the velocity of a river? There you go. What does it mean? Siddhartha sitting here. All right, so what we got here? We're sitting by a river, and we want to say what the velocity of the river is. So does it make sense? Flow rate? Okay, hold on. Really? Yeah, there's a flow rate. Yeah, that's a good idea. Flow rate where? The output? Where's the output? Wherever I start and finish. Okay, but there's like evaporation. What's going on? It's like a little delta. Sorry, I didn't draw my river very well. There's an island here too. There's some inlets here. I'm improvising because I don't like your answer. It's good. It's a good answer. But we'll get to your answer in a second. I mean, if we just say that, then aren't we like missing the ride, right? Didn't we just miss the ride? What's your answer? The moving speed of the water? Okay. moving speed of the water. I'm just saying, have you guys ever gone like whitewater rafting or something? I mean, it's fun, right? You don't want to just say, you finished here. You want to like actually have the experience of going on a raft. Now, if you're on a raft, right, maybe there's like some rapids here and they're really, really fast. And then here, well, I guess if we're being honest, we should like draw the river like to wind a little bit. So it's like longer. It's a very strange river. Okay, and then it's like, going this way. So you can choose, your family went that way, you went this way. And there are certain areas where maybe this is like the faster area. Right? There's more rapids here. And you guys know eddies if you've gone whitewater, right? There's like eddies. Some people, they get caught in them and they go around like that. Yeah, they have fun. So you draw like little arrows. Let's say, I want to say what my river experience was, at least at a particular point in time, or what the conditions of the river are at a particular point in time. To do that, I need to take the whole river. And I need at every point, every water molecule on that river, I need to assign a certain velocity vector and say it's going there. If I do that, I get something called a vector field. And that, I want to say, is the best answer, the most thorough answer to what the velocity of the river is. Sure, it's an impossibly complicated one, but it's an honest one. And we'll see how, with that honest answer, we can then derive these other answers that were very good answers by doing certain types of integrals. Okay, so what is the exact definition that I want to give here? So a vector field is a definition. So a vector field, well, we need to define it on something, on a domain, D, inside of Rn. So it could be n is generally, we're thinking 2 or 3 dimensions, but we really do it in any dimension. It's an assignment, read function, but okay. Of points in D to vectors in Rn. Now, honestly, this is kind of a little bit of a, well, it's not false, but there's more to the story. Let me just say that. There's more to the story about vector fields, but I'm not going to tell you that more story. Let's give an example, aside from just a drawing. Let's give a formulaic example. So oftentimes when we use the notation, what we'll do, I mean, again, in the book, it'll be written like bold, or on exams, it'll be bold. But I can't write bold. I guess I could, but take a little too long. So I put an arrow over it. And you could write a vector field like this. Now, what does this vector field look like? Well, we can draw this. I mean, you can, of course, go to like an online graphing utility quite easily, and it will draw this for you. But for simple formulas like this, it's not hard. So if you're at 1, 0, right, then your vector field F is going to be 0, 1. So it's going to go here. If you're at a 0, 1, you get -1, 0. So you get something like this. Yeah, and then you keep on going. This looks a little too Nazi-ish for me. Yeah, I mean, it wasn't like, intentional, you know. My, this is, look, I'm half Jewish, just, leave me alone. It's actually funny, there are a lot of anti-Semites in math, and which isn't funny, but there was one that I was writing this paper for this journal celebrating him. This guy named, well, I won't tell his name. I mean, it's rumor, it's all speculation, but it's kind of understood. He's anti-Semite. So I I wrote a paper with a graph, and I kind of made like a tree diagram that looked like a swastika. Well, he made his own bed. I'll fill it in so it looks more like what it is. It's not so, right? So hopefully you can see, right? This is going to be a rotational vector field. So if you were to actually flow, and there's a notion of flow with respect to a vector field, where the whole space that you're in moves according to the instructions the vector field gives it, this would be a rotation of the plane. All right. Okay. So a vector field, so not all vector fields are sort of created equally. By which I mean, some vector fields have a very nice property, okay? And they're called conservative vector fields. So let me give you the definition of that, and we'll see throughout the next few lectures why conservative vector fields are such wonderful types of vector fields to be working with. So a vector field F is called conservative. It's nothing to do with any political persuasion at all. If there is a function called the potential, a scalar function, V, I use V, I'm not sure, I don't remember what the book uses, called the potential, or a potential, it's not necessarily unique, of F, such that this vector field, in fact, is equal to the gradient of V. Write that a little more clearly. Okay. So the reason they're called conservative is because they're behind a lot of the forces of physics. So I gave you a picture of a vector field that you could consider to be a velocity vector field. But there are other kinds of vector fields. For example, there are force fields, really, not like in a funny, sci-fi way. There's like a notion of a force field where at every point you put the vector of force. And a lot of force fields are conservative, and that has to do with the conservation of energy. And finding a potential helps, helps solve a lot of problems with these fields. So let's do an example where we see a conservative vector field. So the thing about conservative vector fields is that they're very easy to create. You can just write down a scalar function and take its gradient. It's a little harder on the other side, not impossibly harder, but a little harder if you're just given a vector field to see whether or not it's conservative. Okay. And at this stage, we can just do a couple of things. One is we can just sort of eye it, but let me write down the problem. So let's do a two-part problem. Is f of x, y, z equaling to this vector field minus x squared plus y squared, c squared, y Z. Okay, so is this vector field? Or let's do another one. We'll do a two-dimensional one. Maybe I should use plural here. Are these conservative? And let me write G for the second one so we can not confuse them in the solution. Okay. So solution. So one way of going about this, and certainly at this stage, is just to say, okay, what does it mean? Let's look back at the definition. It means, for this to be conservative, it means there's some scalar function so that these guys are equal to, together are equal to the gradient of the function. So for A, we just say, okay, well, F is conservative if there's a V so that F is equal to the gradient of V, which is Vx, Vy, Vz. And so we can look at, now this is three equations, right? We have three equations. So the first equation gives us Vx equals minus x over x squared plus y squared plus z squared, 1/2. And if you're thinking about this, I mean, so I'm trying to find a function whose partial with respect to x is this function on the right. So do people feel, how do people feel? Is it oh, I'm sorry, guys. I have a 3/2 here. Let me put 3/2. I was wondering, there's something a little on. It won't affect the answer, but I want to put a 3/2 here. Let's put a 3/2. Okay, better. Now that everyone sees that, I'm sure everyone knows. Yeah? Question or solution? Can we integrate with respect to x? If you were to integrate this with respect to x, what would you get? Or maybe integrate is the wrong word. What I mean is antiderivative with respect to x. With respect to x. This should be something you guys could do. Wouldn't this work? The 1/2. Can people read it? No, I mean, I know you can read, but can you read my handwriting? Is it too? Is it clear? Questions? No, okay. No one's shouting on answers, so I'm a little worried. All right, yeah, if I take the partial with respect to x of this guy, I'll get a 3/2 here, power rule, a -1/2 in front, but then I get a 2x, so the 2's cancel and I get a -x. Right. So this is not a hard thing to take the partial derivative of, but now we have to check and say, okay, well, this is a candidate because we have two other candidate potential. There are two other equations that it must satisfy. But when we look back up, we're going to say that the y derivative is equal to this, and the z derivative is equal to this, partial with respect to these guys. And that's all true. This is sort of the same. I mean, it's sort of symmetric with respect to the different variables. You can switch x and y and have the same kind of result. So indeed, we did sort of stumble across just by looking at one of these equations, which happens, you stumble across a potential. So yes, F is conservative. And who recognizes this vector field? Who? Nobody. People like apples, not the computer, like the food. Yeah, okay, good. No? All right, so Newton liked it. Gravity, very good. Yeah, the gravitational vector field, right? GMF. This describes, if you have a single point mass, this vector field is the force field for gravity. And this is the potential, gravitational potential. It says that the gravitational, right? All right, so gravitation. It's also the E&M vector field is for a single point charge. So some of the major examples of physical vector fields are that simple. Of course, this isn't a vacuum and all that. Okay. Now, what about B? Okay, so B is so I've got two G's. One's a vector field. This is the gravitational constant G here. Let's not confuse those. So for B, I want to find some V so that G is equal to the gradient of V, which in this case, I've got a two-dimensional thing. So I've got Vx and Vy. And I look at this and maybe someone can give me a tip. What do people think? Is there a solution here? For this one, let's assume we've solved this. What happens if we take the derivative? So this is G. Let me move it over a little bit. Okay, this is G. Now, let's take a look. What happens if I take the partial with respect to y of Vx? So I'm taking the partial of this guy with respect to y. What is that? 1. Thank you. Good. What happens if I take the partial of y with respect to x? This is Vy. What do I get? 2. Is 1 equal to 2? So no solution. In other words, G is not conservative. Now, here's the thing. And we'll talk about that condition in a second. It's called the cross-partial test that I just applied. If you took a dart and you had the universe of vector fields and you just put them on the wall, okay, and you took a dart and you threw it at that universe of vector fields, you would have a 0 probability of hitting a conservative vector field. Conservative vector fields are sort of measure 0 in the world of vector fields. They're rare, very rare. So they just don't, if you write a random one down, you're most definitely not going to have a conservative vector field. The fact that they occur all over nature is really interesting. Because there's no reason, mathematically speaking, from that perspective, that they should. So in general, if you're handed a vector field, you should not expect it to be conservative. It's not like, well, maybe it's 50-50. No. So how do you detect whether or not they are conservative. Well, that's a hard question, and it's one of the questions we'll talk a lot about as we go. But there's one way we can sort of say right away that it's not conservative, and it's by doing what we just did. And this is this cross-partial test. So I'll do this for 3 dimensions, but of course we just did it for 2 dimensions. You can do it in 2 dimensions, it's a little easier. So if my vector field F, I write it as P, Q, and R. So each of these are functions, not constants, not points. And I say that it is conservative, then, well, I also want to add this very simple condition, but it's usually satisfied. And this condition is that P, Q, and R, we'll say, have continuous derivatives, which almost all of the functions we deal with do. So then it's conservative only if del P del Y equals del Q del X, del P del Z equals del R del X, and del Q del Z equals del R del Y. Just center that a little bit. So this is only, in other words, if it's conservative, then these things happen. However, so this gives you a way of showing that a vector field is not conservative. In other words, if you have a random one, like the one like this part B, and you try this with these functions and they're not, these equalities don't hold, like 1 is not equal to 2, then you know it's not conservative. This is a good test to disqualify functions from being, or vector fields from being conservative. Questions? And I mean, the reason for this, of course, is that if it's conservative, then this is Bx, By, Bz. And when you look at these, you put these into these equations, you're just saying that the second partials have to commute. That's what you're saying. Which is this Clairaut's theorem we had. Okay. So we're going to be talking more about vector fields as we go, as they are sort of this new thing that we are going to be able to integrate over more general regions. This new type of integrand. But I want to say one other thing about vector fields before moving on to line integrals. Okay. So another thing I want to say about vector fields is that, have you guys taken, wait, no, you guys will take ODEs. Is that right? Or some people can take it at the same time. Anyone taken ODEs? No one's taken ODEs. Okay, well, do you know what an ODE is? Who knows what an ODE is? Okay, 1%. ODE, that stands for ordinary differential equation. What makes them ordinary? It means they're differential equations of one variable. Partial differential equations, which are also studied, are differential equations that involve partial derivatives. So several functions of several variables are vector fields. All ODEs, and I think it's fair to say all ODEs, although someone will come and tell me I'm wrong. But nearly all ODEs can be written as one matrix equation with a vector field. And it looks like this. This is a dot. Usually, I mean, you can think of it as d dt. So there is a single, this is a single equation that you can reduce certainly all of the ODEs you'll see in a basic course on ODEs too. Even if they involve higher derivatives or whatever, they can all be reduced to this. And so this equation, and what this equation is, it's an F here is a vector field. And what this equation is a flow equation for the vector field. So you have some vector field in high dimensional space and you want to start somewhere and you want to flow down that river. You want to actually move your particle so that it obeys the vector field. So its velocity is that of the vector field at every point. If you can solve this single ODE, you can basically, well, in principle, or at least as a theorem, you know there is a solution for this, any kind of differential equation you can write like this. And that's almost all of them. Okay, but this is not a class on ODEs, so I just want to expose you guys to that so in the future you'll recognize it. All right, on to line integrals. So there are going to be two types of line integrals that we study. There's going to be line integrals where the integrand is a scalar function, and there's going to be a line integral where the integrand is a vector field. They're called scalar and vector line integrals. There's a variant on the vector one, which I'm not going to spend too long on, but I'll mention it. Now, what is a line integral? How are we generalizing the domain? Well, the domain of a line integral is going to be a curve. And it's a curve, well, usually in 2 or 3 dimensions for this course, but in any dimension in general. So here n again can be 2 or 3 for us. And it may be the case when we do vector line integrals that we want to orient the curve. So we'll talk about orientations next class. So for now, though, let's just assume we have a curve. So what is a curve? A curve, here's a curve. I'll use the letter C, which I know sometimes looks like an E. Sorry about that. This is a curve inside of R2. And now I want to say this is a curve. Now, this is not to be confused with a path. Or now path, I mean a parametrized curve. What's the difference? People know? People want to tell me? Yes. One of them, I heard one of them has a derivative and I heard magnitude. Okay. Yeah, so I think what you're getting at and what you're saying is on the right track, which is that a path has a parametrization. A path says, I've got a function from an interval to this space that kind of tells me at a particular time where I am along this curve. Right? A path is a function, and the image of the path is a curve. Now, that's actually very different. If given the single curve C, I have, an infinite number of paths that gives me this curve C, right? I could go really fast, slow down, so on, right? Or I could go this way. Now, I think the comment was geared at, there's also this path, which is this unit speed, right? Parametrized by arc length. So there is a sort of unique path that moves at unit speed in one direction. But if we don't orient it, we have another one. And if we had a closed curve, we don't actually have uniqueness there either, because we could start at any point. A curve also doesn't have to be connected. A curve could have a couple of different components that are disconnected. Then we have more options. So a path is a parametrized curve. It's a curve with some function that assigns in a one-to-one way points of an interval to that curve. And what we want, the reason to make this clear is because what we want is we want to integrate over a curve. We want to integrate over a curve, not a path. If we can evaluate our integral using a path, but we want it to be independent of what path we choose. And what does that mean? So what we want is a scalar line. And I'll explain what it is. So let's say I take my curve. That's very pleasant. It's your ring? Yeah, that's good. That's good. Keeps you in a cheerful mood. That's good. All right. So let's say I have a curve here. This is my curve C. And this is in the XY plane. And I'm not thinking of it in 3 space. And then I'm going to define a function. And I'll think of f as a function on, say, 3 dimensions, but I can also just start on, not on 3 dimensions, on the plane. But I can also think of it as just a function that's defined on the curve itself. And this is going to be a mass density function for the curve. And I want to find out like how much mass this curve has. So one way I can think about that is I can take sort of the graph of f over the curve, right? Over the curve. This is just a graph over the curve. And I can kind of look at how this thing stretches. Look at this as sort of a part of a surface here. And I can ask for the area of that. So what is the area? That quantity, whatever it is, does not depend on how fast I'm moving along that curve, right? Or which direction I'm going on that curve. It just depends on the curve and the function f. That area is not going to depend on a parametrization. It's just dependent on the curve and the function. And that area is precisely the notion of this scalar line integral. So the answer to that question is the scalar line integral, but let's flesh out a little bit what it is. Well, if I want an area, so if I want an area and I do some approximation, then what I'm going to do is I'm going to do some Riemann sum. So right here, I sort of split this curve up into little subcurves, right? And along each of these little subcurves, I can look at just this part. And I can look at an approximation of that area. So I'll partition it up and I'll say, okay, I've got a del S1, S being sort of the length of these bases, del S2, del S3, so on. And I can say, okay, well, this is going to look a lot like the sum of f of pi del Si, where here, again, I choose, let me give myself a little color. I'll choose a P1, P2, a point in each of these little subcurves. And over that point, I'll find a height. So I'll make a little curvy rectangle here over each of these. Now, the question is, so what are these del SIs at this point? So here, we're going to go from I equaling 1. Well, del SI is the length of that little subcurve. And we can approximate that by saying, okay, let's say now we have a parametrization of this curve because we want to do a computation. Let's take the derivative of that parametrization. Maybe we can do it at pi, sorry. And then let's multiply by del x. Change. I think I used, oh, sorry, I should use t here. T. Sorry. So here, this is when R is a parametrization of the curve. And what is that saying? So why do we have such a estimate? Well, it's saying if I'm moving along that curve via R, and I want to approximate how far I go for a very small distance, I can take my velocity at the starting point and multiply it by the time that it lasts. And that'll give me the distance I cover, approximately. Sure, if I'm turning a lot, that will be off, but if I make it very small, then it will be close. Make my time or distance very small. So if I do that, then, and I say my point, well, then what I'm going to get here, if I take the limit of these, I will get, well, let's say my point that I take in is now, because I have this parametrization, it's going to be R of t by, we'll choose the endpoint here. This will be R prime of t. You can see that what you get here is you get this function integrated as a one variable integral. So this is just the definition of a one variable integral from a to b of this function, f of R of t times the speed. Okay. So, okay, so you might rightly question, my sanity here. I'm sitting here telling you it doesn't depend on parametrization, doesn't depend on parametrization, doesn't depend on parametrization. And all of a sudden, I throw in a parametrization. Okay, well, it doesn't depend on this parametrization. But if we want to compute it, what we do is we find a parametrization and compute. The point is that if we had chosen a different parametrization, we would get the same answer. Okay, and so that's something I want to emphasize. All right, it looks like I'm about out of time, so we'll stop here, pick up Thursday. Please do send questions for the review, though.